Hello everyone, welcome to the channel. So in this playlist I'll be solving important questions related to linked list. So my whole motive creating these videos is to practice my problem solving and implementation skills along with my communication skills. So hopefully I can achieve both of them together by creating some videos as well as uploading them on YouTube. So let's go. So today's question is merge two sorted linked lists. It can be found on LeetCode. It's LeetCode number 21. LeetCode 21. Merge two sorted linked lists. So basically what the question says is there are two linked lists. So the brute force or the first approach to this problem goes like this. We have two lists. One list has a h1 pointer pointing towards the head of that one, and for the other list there is h2 pointer pointing towards the head of that list. So we first create a dummy node. Now what does this dummy node do? We will first compare which one of these two has a smaller value. In this case, either of them, we can take either of them, but let's suppose we take h1's the smaller value. So we will create a new linked list and put the h1 dot value at value of that node to which h1 is pointing currently and put it in the new linked list. Now what we will do is make the next of this dummy node point towards this value, and then we can create just a duplicate of this dummy node which will keep on traversing in the new list. Once the first node has been taken out from the first linked list, now we can move the h1 to this node, and now the comparison will be done with this one and this one. The one which is smaller comes to the next of the current position of the temp and gets placed here. Now we create a new node, put the value of the smaller one out of these two and place it here, and then move the temp, the duplicate, basically the duplicate of the dummy node, to here. Remember that we have to keep the dummy node here, and we have to move a duplicate of that dummy node throughout the list. That is supposed to be the answer. Now since we have used this one, we will move the h2 pointer now pointing to this. Now we will compare with these two. The similar process will continue till one of the list ends. So now I have completed the whole answer list in which I kept on continuing that process of comparing one node from the list 1 and one node from the list 2, and out of which the smaller one gets a place in our answer list. So after getting this linked list as the answer, we just have to return the dummy node dot next. And since linked list works on the basis of addresses, when we return the dummy node dot next, it will subsequently return the whole answer list and will get printed on LeetCode. So the approach that we discuss right now will give a time complexity of big O of L1 plus L2 and the space complexity of big O of L1 plus L2. Why L1 plus L2? It's because in the worst case we might have to traverse the whole of list 1 and the whole of list 2 as well. And the space complexity is really easy, where we are just extracting one element at a time from each of the lists and putting it into the resultant list, and hence the space complexity of is L1 plus L2. So is this the best solution? No, because we are just using each of the elements and putting it into a separate list, the resultant list, and that is creating this space complexity. So what we have to do is we have to eliminate this space complexity and do such a solution that there is no extra space complexity. So basically what we are trying to achieve is we are trying to achieve an in-place solution. So what if we just do the solution in the linked list itself, both the linked list itself, we break the links in such a manner that the combination of both the linked lists is the answer itself. So how do we get a more optimal solution to this, or the in-place solution? So let's look at this. So these are the lists. So what we can do in the in-place algorithm is that we can break these subsequent links and make the next links in such a manner that the combination becomes the resultant. So 1 is connected to 2, but 2 is connected to 6. What should be the next one? 3. So we will just break this link and the node dot next value will go to this. 3 is connected to 5. Yes, it is. But 5 to 7 does not look right? So it will connect it to 6 and subsequently break this link, and then this will get connected to this one and break this link, and then this will connected to this one, break this link, and then subsequently the whole list will be arranged in such a manner that this is the answer. So in this approach we are going to have two variables, namely L1 and L2, and the very important, or let's say the main point of this algorithm is that we have to always keep in mind that we have to keep one of these variables, let's say in this case we assume it to be L1, we will keep L1 to be the smaller one. Okay, we will keep the L1 to be the smaller one. Out of these two, the smaller one is 1, so we will keep this L1 pointing towards 1 and the L2 pointing towards this one, 3. Okay, so then what we have to do is we will keep a temp variable. What is the work of this temp variable? This temp variable basically tells us that which one was the last smallest element that was in L1. Okay, which one was the last smallest element that was in L1. So in this case, how the loop will run? We will run the loop in such a manner that L1 stays smaller than L2, and it breaks the loop when L1 becomes greater than L2. Okay, so let's see how this thing is going to work out. So we have these two lists. We point L1 to the smaller one among them and L2 to the larger one, the 3. So, and we have this temp node, and we assign null value to it. So now we start comparing L1 and L2 and keep on comparing till we get L1's value to be greater than L2's value. So now that L1 is 1 and L2 is 3, so we will move L1 ahead. Now L1 points towards 2, but in the process when it moves ahead, it will keep the record of the last value of L1 inside temp. Now it will compare L1 and L2. Now it's still lesser than L2, so before moving it will then keep record of the last smallest element in L1, and now it will move L1 to the next one. Now at this moment we realize that the L1 exceeds the value of L2. So now what we have to do? When we realize that L1's value has exceeded the value of L2, what we will do, that we have this value temp that is pointing towards 2. So what we will do, that we will make the temp.next pointing towards L2. Now this is a new chain or a new link, you can say. In this new link we have broken the previous link that said like 2 was pointing towards 6, now 2 is pointing towards 3, and the moment we do this we just swap the values of L1 and L2. So why do we swap them? Because if you remember, in the beginning we discussed that we have to always keep the L1 at the smaller one. So now we will keep this as L1 and this as L2. So this marks the ending of the first iteration. Now again, when the next iteration starts, the temp value again becomes null. Now again the same process continues. We have to keep on moving L1 till it exceeds the value of L2. Now that it will compare L1 and L2. L1 is smaller, so the value of temp will get updated and the new value is 3. Now it will move ahead here on 5. Which one is smaller? L1. So we will have an updated value 5. Now it will move ahead. Now we get to know that the 6 is now smaller than 7. Now a new link will be formed. We will just put the temp.next again point towards L2. Now the moment we put this new link, we again swap L2 and L1. Why? Because we discussed this earlier. We have to keep L1 at the smaller one. Remember, we have to keep L1 at the smaller one. So now this marks the end of the second iteration. When the second iteration ends, we now have a temp value of null again. So we compare L1 and L2 again. L1 is smaller than L2, so we update temp's value to be 6. Move L1 again. Now we know that L1 has exceeded L2. So what we do is create a new link, temp.next points towards L2, and then swap these two values again. Why? Because we have discussed earlier that L1 should always point to the smaller one. When we swap, it marks the end of the third iteration. Now the fourth iteration starts. So when the fourth iteration starts, we have the temp as null, and we compare L1 and L2. L1 is smaller, 7, so we update it. Now the value is 7. Now what we do is move the L1. The movement L1 reaches null value, what we do is we point the temp.next towards the last remaining node, that is 8, and hence we get this path which is our answer: 1 2 3 5 6 7 8 null. And you can see this is a merged sorted linked list. In the beginning we could have done a node, or let's say variable, which would point towards the beginning of L1, and we can return this res, and hence that is our answer. So now let's look at the Java code. So in the Java code, the function is given with two lists, the L1 list and the L2 list. So if the L1 list is equal to null, the answer will be list L2, and if the L2 is equal to null, the answer will be L1. These are basically the corner cases that we have to take care of. So in the optimal solution, we discussed that we have to keep the L1 list to be the smaller one. So by any means or by chance the L1 exceeds the L2, or let's say it is greater than L2, then we have to perform this swap operation so that L1 becomes the smaller one. Then comes the next part of the code. Now we point a pointer towards L1 and we run a loop while L1 not equal to null and L2 not equal to null. So basically it will run till either of them ends. So we make a node temp and assign null value to it and run a loop. Run a loop L1 not equal to null and L1 dot value less than equal to L2 dot val. So basically what this while loop does is it keeps a track of the last node that is there and keeps on moving the L1 to the next. Then after this loop gets over, we know that we have the end of L1, and now we can just attach the temp.next to the L2. What this does is attaches the remaining of the list from L2 to L1, and now we just have to swap L1 and L2. Now after all this is over, we can just return the resultant and we can get our answer.